Hey guys, today I'm going to cover the heating and cooling curves. So, what are some of the things that happen as we heat a sample up? So, as you are adding some heat, the thermal energy to a system, what does actually happen at the molecular level? So, let's go and take a look at this. That we have a beaker filled up with water and ice, and we are going to be adding the heat energy to this system and see what happens. Well, we know that initially we start with a solid, right? Because we have ice cube here, which is a solid form of water, and then eventually, when you add enough heat energy, they're gonna melt down and becomes a liquid. And then eventually, when you add enough energy, they're gonna turn into the gas as they evaporate. So these are going to be the phase change from solid to liquid to gas, and then we are going to have a specific name for each phase change. Okay, so when solid turns into a liquid, which is the first arrow, that's called melting, and then the next phase change is from liquid turning into the gas, and this is the second arrow, and this is called evaporating. And as you're adding more heat energy, right? This is also to say that there is an increase in entropy. While the entropy is the vocab word we're gonna cover later, but entropy basically means that it's like disorder and how something is messy. We are actually able to numerically evaluate how messy something is. Okay, just put it this way: when you have a water molecules put together, right, into the confined space and solid, we're gonna say that relatively it's pretty organized. But as you add more heat energy, things begin to shake up, and then some of the solid will turn to the liquid. Now there is more mobility to the water molecules, and they're more free to move. So we're gonna say that there is more messiness. Okay, it's not as organized as before. And eventually, when you have enough heat energy, all the water will just break apart from each other and becomes gas, which is total just chaos and total disorder. Okay, so when you're adding more heat energy, typically it's going to create more entropy. Okay, what is the heat and how is the heat different from the temperature? Well, heat is a measure of kinetic or translational energy. So heat is a form of energy. In chemistry, heat is measured in joules. Heat is dependent on the mass, temperature change, and specific heat. Okay, and to calculate the heat energy, we are going to be using this equation. Q is equal to mc delta T. Temperature is a measure of a warmth or coldness. Temperature is not, therefore, the same as heat. Temperature is not an energy, it is just a measurement. And temperature is measured in Kelvin or Celsius. Okay, what is the heating curve? The heating curve is a graph, okay, which represents how a sample changes the phases. As heat is added over time, the sample changes temperature and the phase accordingly. Thus, it's called the heating curve. So it's basically a graph to represent the phase change as the amount of heat energy increases or decreases. Okay, how does a heating curve look? What does a heating curve look like? It typically looks like this, okay? And you need to keep that in mind. It's going to be a graph, and the y-axis typically a temperature, and x-axis is typically the time progression of the reaction. And there are going to be usually 5 sections. The first sections, second, okay, the first one is increasing, second is actually flat, third one is also increasing, fourth one is flat, and the fifth one is also increasing. And what are the parts of the heating curve? Okay, let's go back to this heating curve. The first section, okay, the first section, remember, is increasing. This is what we call them a solid phase. So this is when the given substance is cold enough to stay solid. Then the third section, right, which is a second increasing section, the first increasing and the second increasing. This is called the liquid phase. And then the fifth section, which is all the way top here, another increasing section, this is called the gas phase. And the second section, or the first flat section, is called the melting. And then the fourth section, or the second, the flat section, this is called evaporation. Okay, the change of state. And this is going to be, again, another representation of the heating curve. Okay, the first section, which is increasing in temperature, this is called the solid. That's when the particles are organized nicely and they're all put together. So we're gonna say that this is where the entropy is the lowest. Entropy means a measurement of randomness and a measurement of messiness. And then the second section is a flat. So what's happening over here? Even though we are adding more heat energy, the temperature is not changing. That's because all the heat energy we are inputting to the system is used to actually change the phase from solid into the liquid. Okay? And then as you go from left to right, this is called melting. And if you go from right to the left, it's the opposite, which is freezing. And the third section is now another increasing section of the graph, and this is called the liquid. That's when all of our given substance has turned into the liquid. And as you can tell, now some of the molecules are more free to move. So there is a higher quantity of entropy compared to the solid. And then there will be a second section of the flat. And this is again when the temperature does not change as you add more heat energy. That's because all the heat energy is being used to turn the liquid into the gas, which is another phase change. And then eventually the last section is going to be again increasing the temperature as you had more heat energy. And that's when every particle has turned into the gas. Okay. Why is the curve flat at some portions, such as the second and the fourth sections? Well, the temperature is staying constant because the heat energy is used to change the physical state. Okay? During this time, the phase change occurs rather than increasing the temperature. So, rather than the heat energy used to increase the temperature, this is when all the heat energy is being used to break the intermolecular force that's holding the molecules together. Okay, so remember when you're in solid, there is a lot of intermolecular force, meaning the interaction between the molecules hold them onto each other, therefore becoming the solid. So now the heat energy for the first section, what we call the melting, that's when all the heat energy is used to melt the intermolecular force between the water molecule to break them apart, rip them apart, and turn them into the liquid. That's why the temperature doesn't increase. And there's a special name for this. This is called a heat of fusion, okay, in segment BC. So the second section here, this is called a heat of fusion. Okay, this is the amount of heat energy, okay, that's required to melt or freeze. And then the fourth section here in the graph is DE, segment DE. This is called heat of vaporization. This is the amount of heat energy required to evaporate your sample. Remember, fusion is melting and vaporization is evaporation. What is heat of fusion and what is the heat of vaporization? Heat of fusion, which is going to be written shortcut delta H fuse, which is for fusion, is the amount of energy needed to completely make a solid into a liquid. And delta H vap is the amount of energy needed to completely make a liquid into the gas. To calculate the heat energy for melting and freezing, you are going to be using this equation, okay? Ignore that square, okay? Just the Q, okay? Q stands for the quantity of heat energy, which is by the M delta H fuse. So the M is going to be the mass, and the delta H fusion is going to be constant value. And to calculate the heat energy for evaporation and condensation, you are going to be using the Q is equal to M delta H vaporization. Again, the delta H fusion and delta H vaporization is going to be constant. Okay, it's going to be a unique number for every matter, and I am going to give you this handout, okay, so that for as a reference. You may use this handout for your chapter exam, okay, and for your homework and so on. So keep that in mind. You need to actually first see what kind of matter we're dealing with, okay, and this is one is going to be for heat of fusion. So if your sample is turning from solid to the liquid, you got to look at this section. Okay, so you need to look at two different things. You need to look at the melting point, the temperature, and also the heat of fusion, which is given in joule per gram. And the bottom one is going to be for heat of vaporization. Same thing, you need to look for the boiling point and heat of vaporization. Practice problem. What is the heat in joules required to melt 25.0 grams of ice? So how much heat do we need to melt down 25.0 grams of ice? Since you are melting, we are going to be using this equation. Q, the heat amount of heat, is equal to mass times delta heat of fusion. The mass is 25.0 grams. Oops, this one's typo. This one should have another 0.0 here. And then multiplied by the heat of fusion for the ice, 334 joule per gram. I got this number from this handout, right? For the melting, for the water, right? We are looking at the heat of fusion, 334. That's how I got this number for. So I'm going to go ahead and multiply these two numbers, reporting your answer in three significant figures. You get this number. If 3.25 times 10 to the fourth power of joule of energy is available, how many grams of water can be evaporated? Well, we're doing the evaporation this time. So I'm going to go ahead and use down this equation. Q is equal to M delta H vaporization. And then since I'm trying to solve for the mass of the water, I'm going to rewrite the equation in terms of M. M is equal to Q over delta H vaporization. And energy is given to us divided by the heat of the delta H of vaporization of water, right? Which I can again get from here. And since we are doing the vaporization, I'm going to look into the water and I'm going to look at this number, 2,256. So we got this number divided by, reporting your answer to the three sig figs, and you get a 14.4 grams. Now, this is a heating curve practice problem, and this is where things get a little messy. How much heat would it take to raise the temperature of a 1.00 gram of water from negative 25.0 Celsius to 73.0 Celsius? Okay, now you are given a initial temperature and final temperature, okay? So you have to find out exactly which phase change this water, this 1.00 gram of water is going to experience. So the best way to do it, draw a heating curve. Okay, first go ahead and just simply draw the y and x-axis and then draw the 5 sections like this. I don't care how long each lines are, it doesn't really matter. We just need 5 different sections that looks like this. Then you need to first label melting and freezing point. This first flat portion, right, segment BC, represents when your sample is going to melt or freeze, okay, depending on which direction you look at from. And then label the second section here. This is where your sample is going to boil or condense, depending on perspective, okay? And then you have to now go back to your reference handout, here, and then look for the water, okay? Water melts at 0.00 Celsius, and water also boils at 100.00 Celsius. So I'm going to go back to my heating curve and then label those. Okay, so the melting point here, right? The melting point for the water, which is this section, is going to be 0.00 Celsius. And for the boiling part, right, this is going to be labeled 100.00 Celsius. And then, based on the question, you're starting from negative 25.0 Celsius. So if this is 100, this is 0, right? Negative 25 has to be somewhere below 0. So again, it doesn't matter where you mark, but I'm going to just randomly put it somewhere here. I'm going to go ahead and say this is exactly negative 25.0 Celsius. And you're ending in 73.0 Celsius. 73 must be found somewhere between the 0 and 100. So I'm going to go and randomly just point it right here. 73.0 Celsius is going to be right there. So you're starting from negative 25 on the heating curve and ending on the 73.0. So that means I'm going to be writing the heating curve, this section, right, to go from negative 25 to 73. I'm going to start from here. Here's my first section. Then here's my second section, and then third section. Okay, so this problem, you're gonna have to solve the amount of heat energy required to go through these 3 sections. The first section is going to be what we call them amount of heat energy used to increase the temperature of the ice, because this is the ice section, right, the solid phase. Then the second section is going to be called the Q of fusion, amount of heat energy required to melt or freeze, or actually in this case, the melting, because you're going from negative 25 to 73, lower temperature, higher temperature. And the last section is called the Q of water, or the liquid, right? Because this section, the CD segment, is the liquid section. So the amount of heat energy total is going to be by adding these 3 sections. Amount of heat energy used to increase the temperature of ice, to melt the ice, and then increase the temperature of water. Okay, amount of energy required to increase the temperature of the ice, which is going to be MCAT, MC delta T. Okay, and then you are going to be using 1.00 gram of water mass and the specific capacity of the ice, which you can get it from the reference handout I'm going to give it to you, which can be found out 2.010 joule per gram per Celsius. And then change of temperature, which is a final temperature minus initial temperature. Okay, initial temperature is a negative 25.0. But where is that 0.0 comes from? I said the final temperature minus initial. Well, then shouldn't I be putting the 73 here? No, that's because we are dealing with the ice phase only. Let's go back to this graph. Ice phase is right here, right? The water is only ice when they are under 0.0 Celsius. So the moment we reach out to 0.00 Celsius, it's going to go to the next phase and go to the melting phase. So the ice phase is only from negative 25.0 Celsius to 0.00 Celsius. So this is your beginning temperature. This is your final temperature for this segment. So I'm going to say that the final temperature is 0.00 minus 25.0 Celsius. You multiply everything according to Sigvig rules, you get a 50.3 joule. Now, the Q of fusion is easy because it's going to be mass times delta H of fusion. Mass is 1.00 gram, and the heat of fusion you can find from your reference handout, and you get a 334 joules using 3 Sigvigs. Lastly, the amount of heat energy used to increase the temperature of the water is going to be also using the MCAT. Okay, so whenever you are using the increasing graph, right, you're going to be using the MCAT. Whenever you're calculating heat for the flat portion, you're going to be using something like this. Okay, so mass is 1.00 gram. The C is the specific capacity, which also can be found in your reference handout. And delta T, final temperature minus initial temperature of the water. Okay, so according to the graph, that's this section, final temperature is 73 right here. Initial temperature is 0. Remember, you are moving this direction, right? So this makes your final, this makes your initial for this segment, right? So 73 is the final, 0 is initial for this segment. So you then calculate your answer for that and simply add them all together. Using the significant figure rules, you round your answer to nearest ones. And this is it.